Here we'll draw a graph of a polynomial, this time given a function. Our polynomial function is 1 over 24 times x plus 1 times x minus 2 to the third power times x plus 3 to the second power. We can tell this is a polynomial because we have a series of binomials in parentheses written as a multiplication chain. Anytime you see that, you're dealing with a polynomial. To begin with, we're going to find the x-intercepts of this polynomial. And to find the x-intercepts, we will set each piece equal to 0 that's in those parentheses. So in our parentheses, we have x plus 1, x minus 2, and x plus 3. We'll set each of them equal to 0. For our x plus 1, we will subtract 1 from both sides, giving us x equals negative 1. If we do the same to our next piece, we'll have x minus 2 equals 0. We'll add 2 to both sides and get x equals 2. Do the same with our final piece. We have x plus 3, so we subtract 3 from both sides and get x equals negative 3. Therefore, we will mark those intercepts on our graph at negative 1, 2, and negative 3. We can also make a note of how we would expect them to cross through based on their multiplicity. To find the multiplicity, we will look to the powers above each of these parentheses. You may remember from our previous video that if we have a first power piece, like we have here for our x plus 1, we could expect that to cross straight through. So at negative 1, we could expect the function to go straight through. We don't quite know how it's going to do that yet, but we know that's what will happen. At our x minus 2, we have a third power, and remember from our previous video that if you have a third power, we can expect that to squiggle. For our last piece, we have x plus 3, which is second power, and we know if we have a second power, we can expect that to touch, but not go through. Therefore, we'll write at each position what we can expect the function to do. At negative 3, it will touch, but bounce back off. At negative 1, it will cross, and at 2, it will squiggle. Of course, this is all based on the powers in the original polynomial function. For our final step, we can also get the y-intercept as well. For our y-intercept, we will plug in x equals 0 and see what y we end up with. We will now rewrite our polynomial function and place 0 in place of each x. Now we handle the arithmetic. We'll start by writing 1 over 24. We multiply by 0 plus 1, which is 1. We multiply that times negative 2 to the third power. Negative 2 to the third power would give us negative 8. And then we'll multiply that by 0 plus 3 squared, but 0 plus 3 is 3, and 3 squared is 9. If we multiply all of this together, 1 times negative 8 times 9, we will end up with negative 72, and we multiply that by 1 over 24. If we do this multiplication, we'll end up with negative 3. This means our y-intercept will be 0, negative 3. We'll place that on our graph as well. Now that we've marked down all of our intercepts, the only question left is what is the function going to do on the left and the right? We'll ask ourselves this because we already know what's going to happen at each of the intercepts. We know the line must go through each of the red dots we've marked, and we also know how it's going to cross. But what we don't know is where the function comes in from and where the function exits. We don't know what the left and right ends of the graph look like, and so now we'll investigate the end behavior. The end behavior of a polynomial depends on whether the leading coefficient is positive or negative, and also whether the power of the function is even or odd. if you have a positive leading coefficient and an even power function, the function will come in from positive infinity, it's going to squiggle around some, and then go back up toward positive infinity. If your a coefficient was negative, it will instead come in from negative infinity, do a bit of squiggling, and then go back down toward negative infinity. However, if you have an odd power function and a positive coefficient, you'll come in from negative infinity, do your squiggling, and then go up toward positive infinity. However, with a negative coefficient, you will do the opposite. You'd come in from positive infinity, do your squiggles, and go down toward negative infinity. Let's have a look at our function now. Our leading coefficient will be the fraction in front. That's 1 over 24. We don't mind that it's a fraction, we only worry about the sign, and that is a small positive number. Therefore, we will say our a is positive, and so we know it must be either the even positive or odd positive outcome. Now we're going to look to our power. We notice that in our function we have a 2, a 3, and then an invisible 1 over the x plus 1. This means our power for the function will equal 1 plus 3 plus 2. We simply add the powers of each member of the chain together, not counting the leading coefficient. 1 plus 3 plus 2 will give us 6, which is an even number. Therefore, we have a positive coefficient with an even power, which means our graph should look something like this. Our graph will come in from positive infinity and also exit at positive infinity. With this in mind, we'll now draw our graph. Because we had a positive coefficient and an even power, we will enter and exit from positive infinity. To symbolize this, we'll draw our upward arrows on either side. Remember that at -3, we had a second power, and so we can expect that to touch but bounce off. So the graph will come in from positive infinity, it will touch -3, and come back up. Then, at x plus 1, we had an invisible first power. That means we will cross through. So the graph, once it has gone back up, will come back down and cross through -1. We'll continue going down at least until 0, -3. Then at some point, we're going to have to turn back and hit the 2 here. The power on that 2 is third power, which means we can expect it to squiggle as it goes through. Therefore, we will go through the 2, making the squiggle shape, and making sure we exit at positive infinity. Notice as I drew, I failed to hit this arrow I provided for myself earlier. That's okay, you can just erase it if you miss. Again, this does not have to be a perfect graph. The important thing is to make sure that we get the end behavior right. That means both of these arrows must go toward positive infinity, and we must touch the axis at the right places and cross through the way that we're meant to. Thank you for watching. We'll see you again soon.